Alright, welcome. In this video, I'm going to be working the Algebra 2 Unit 7 review. First problem, this is a problem type you should be familiar with and ready to work with on the test. Write the 4-3 polynomial in standard form with zeros at x equals -3, x equals 0, and x equals 1 plus I. Okay, what we learned is that if x equals 1 plus I is a root, and we're going for 1, and it didn't say, but it meant to say 4-3 polynomial function with rational coefficients. Okay, and we're looking for all of these zeros, then we'll also have to have x equals 1 minus I as a root. So if I've got these roots, then I've also got these factors, x minus -3, x minus 0, which I'll just write as x, and then x minus 1 plus I, and x minus 1 minus I. Right, so I'm going to distribute those negatives, and maybe also distribute the x to the x plus 3, so I'd have x squared plus 3x, that one, then x minus 1 minus I multiplied by x minus 1 plus I. Okay, now to do the ones with the i's in them, I think we can do that off to the side with a box. X minus 1 minus I multiplied by x minus 1 plus I. Okay, and there we go. Okay, we filled out the box. I'm going to have an x squared. X's, I'd have -2 of them. And I'd have plus 1 minus I squared would be plus 2. Okay, that's what we're looking for there. And just like always, when we bring in the conjugate and we multiply that out, all of the stuff with the i's, just cancels off. So I'm going to erase all of that and say I've got x squared plus 3x multiplied by what I've got here. And, this might be a good time for another box. X squared -2x and positive 2 multiplied by x squared and 3x. Okay, there we go. And then I'm just going to kind of report my result is going to be x to the 4 plus 1 x to the 3, because I had -2x to the 3 plus 3. So it's positive x to the 3 minus 4x to the 2 and plus 6x. Okay, and that's going to be in standard form. Nobody said anything about the leading coefficient, so I'm just going to assume it's 1. If they had said what the leading coefficient was, I would have probably just dropped it in right there and multiplied it in at the end. Okay, so that's how we did that one. Okay, this next problem is a quadratic, and it's asking you to sketch the graph. This is probably not a problem type you are going to need to worry about on the test, because we haven't done one like this in quite a while. It doesn't seem familiar. So it says find the zeros. So I'm going to try to factor, but I can't think of any factors of 4 that add to 2. 4 and 1, 2 and 2 is not going to work. So I'm going to choose the quadratic formula. I'll see x equals -b plus or minus the square root of b squared minus 4 times a times c is 4 times 1 times 4 all over 2a. Okay, now 4 minus 16 is -12. And maybe off to the side I'll say the square root of -12 is the square root of 4 times the square root of 3 times the square root of -1, which I might call 2 root 3i. Okay. And so if I was to divide that whole numerator in half, then I would divide both of those things in half, so I'd have -1 plus or minus square root of 3 times I. So those are going to be my roots. And since this thing has got a positive y-intercept and no roots, has no x-intercepts, I know it's going to be an upward-facing parabola that never intersects the x-axis. Okay, I think we could see that, oh, the x-coordinate of the vertex would be negative b over 2a, so it'd be negative 1. So I know that the y-axis is going to come over here, let's say about like that, and that's going to be a good enough sketch for us. Alright, rational root theorem is not part of this unit, so, feel free to skip on to the next one. I'm going to work this problem because it's never a bad time to review something we've already done in this class, but I'm going to tell you that the rational root theorem is not on this unit, it's not on this test, you don't need to be worrying about it right now. Okay, so the roots would be p divided by q, where p is a factor of 36. Let's see, factors of 18 could include 9, 6. Okay, then there's also going to be 12. Okay, so 12, 9, 8 does not divide 36, but 6 does. This is exactly the type of problem I tried to avoid giving you this year. Plus or minus 2 or plus or minus 1. Alright, so you can see that there's gonna be a lot of overlap here. I guess I will write them all out. So plus or minus, I'm gonna need more room than that though. Plus or minus 36 over 1, plus or minus 36 over 2. Well, that's already 18. Plus or minus 12. Plus or minus 12 over 2 is 6. That one's already going to be on the list. I'm good. 9 halves. That's one that isn't on the list yet. Okay, so I'm just kind of looking for all the other ones that that are odd, I guess. Because I need to remember to possibly divide by 2 for that one. Okay, so 3 halves. Plus or minus 2, plus or minus 1. Plus or minus 1 half. Yeah, that's not going to be on the test. Alright, find all solutions of the following equation. X to the 4 minus 5x to the 3 plus 8x to the 2 minus 20x plus 16 equals 0. What are we starting with? Okay, no graph. No hint about what the roots are. Okay, remember in my class I'm going to start you off with either the graph or the roots or the fact that the... Oh, no, x equals 1 is a root here. Okay, didn't even forget about that. Try, rational root theorem. Start with x equals 1, right? And that usually works for us. I think it's going to work out here. So we're just going to try it and hope for the best. So it would be negative 4. That's not going to be negative. That would be positive 4, yeah. And then here we go, negative 16. There we go. Okay, and yeah, we can find all the solutions because this is going to be factorable. So I have x minus 1, I just divided away, and what I'm left with is an x to the 3 minus 4x to the 2 plus 4x minus 16. Okay, I'm still trying to find where this equals 0. So I'm going to continue factoring, doing a little bit of group and factor. We've been doing a lot of this lately. Plus 4 times x minus 4. Okay, and factor out the x minus 4, left with an x squared plus 4. Now I've got it fully factored. I've got x equaling 1, x equaling 4. From x squared plus 4, I'm going to have x equals 2i and x equals negative 2i, right? Because if I try to solve that for x, we get plus or minus the square root of negative 4, and that's going to be 2i and negative 2i. Okay, yeah, that was number 4. Alright, a fourth degree polynomial has this graph, describe the number and types of solutions. Okay, well, it's got 2 real roots right here. And it's going to have 2 imaginary roots, and they are going to be conjugate pairs. Sixth degree polynomial. Yeah, I've got 1 single root, 1 double root, and a second single root, so that's a total of 4 roots, 6th degree, so I've got 2 imaginary. For real, split out into 2 singles and 1 double. Okay, and that adds up to 6, right? So, because it's a 6-degree polynomial. Right, find the value of the absolute value of -5 plus 12i. Okay, so I'll draw you a picture. That's not where the imaginary axis should go. -5 plus 12i, maybe I want it to look like that and move it a little bit. Okay, -5 plus 12i. Okay, that's the point. Absolute value of this number is the distance from the number to 0 on the complex plane. Okay, so what we're going to do is we're going to set up a little triangle and think about the lengths of that triangle. Okay, and this distance here is going to be equal to the square root of -5 squared plus positive 12 squared. And we don't really need the negative on the 5. We could just say 5 squared plus 12 squared. If you know about 5, 12, 13, that's Pythagorean triple, you could say, okay, this is going to be equal 13. If you don't, then you'd square -5, you get 25. Square 12, you get 144. Add them together, get 169. Square root of that is 13. Okay, so then the next one, express these numbers in terms of I. You can do that. Okay, that's probably not going to be enough room for me to work, but 125, I have to just think about what are factors of 125 that are a perfect square, and definitely 25 is coming to mind. So I think, what do I multiply 25 by to get 125, and that would be 5. And then I've still got that negativity, so I'll just account for that with a -1. And so the square root of 25 is 5, square root of 5, I can't really do anything with that, square root of -1, that's I. And for square root of -8, I think about, okay, what are the factors of 8 that are perfect squares? And I'm thinking of 4. So I'm going to say it's 4 times 2 and the -1. Okay. So the square root of 4 is 2. -4 times 2 would be -8. Square root of 2 multiplied by I. 10 square root 49, okay, well I'm just going to say that's 10 times the square root of 49 times the square root of -1. And that's going to be equal 10 times 7 is 70i. The square root of -75, okay, that's divisible by 25, so I'm going to use that. Square root of 25 times the square root of 3 times the square root of -1, that's going to be 5 root 3i. And the next ones are just kind of, some arithmetic, so we're going to subtract these two. We're going to do that by distributing a negative. So 3 plus 1 is 4, 6i minus 9i is -3i. Okay, we're just distributing that negative to both of those terms and then adding. Okay, this is going to be a multiplication, so I'm going to do FOIL. 6 times 2 is 12. 6 times -5i is -30i. 4i times 2 is 8i, and 4i times -5 is -20i squared. 8i squared is -1, so I've got 12 minus 20 times -1 minus 30i plus 8i, so I've got 32 here and -22i. And here we've got some division of complex numbers, and we divide by multiplying on top and bottom by the conjugate of the denominator. So if I've got 5 plus 2i in the denominator, I need to multiply on top and bottom by 5 minus 2i. And that will turn the denominator into a real number, and then I'll be able to, actually divide it out and write this as some number plus some other number of i's. So I'm going to do a little bit of foiling on top. 3 times 5, 3 times -2i, 12i times 5, and 12i times -2i would be -24i squared. And then I'm dividing by 5 plus 2i, 5 times 5 minus 2i would be 25 minus 10i plus 10i minus 4i squared. So I've got a 25 plus 4 in the denominator. After the negative 10i and the positive 10i, they add to 0. And then, okay, 15 plus 24 would be 39. And plus 54i, okay, divided by 29. So that would be 39 over 29 plus 54 over 29 times I. That was kind of a lot, but that's something that we need to be able to do. All right, the next one, 3 plus I plus 2 minus 3I. I don't know, you could just rearrange them and combine like terms. That's all we're doing when we're adding complex numbers, is combining like terms. F1 minus I squared is going to be okay. Just got to remember to do 1 minus I multiplied by 1 minus I. And then do FOIL. 1 times 1, 1 times negative I times 1. Negative I times negative I is positive I squared. And then I get 1 minus 2i plus a negative 1, so I squared, and then I just get negative 2i. G, H, I, and J are these, higher powers of I. Remember we told you to solve these by, if it's an even number, just dividing it in half and seeing if half was also an even number, just, kind of writing it as a power of I squared. And if it was odd, breaking off the one of the powers, the last power, and then dividing in half. So I to the 55, what I'm going to do with that is I'm going to write that as I to the 54 times I to the 1. And then that I to the 54, I'm going to divide it in half and say what's half of 54 is 27. I write it as I squared to the 27 times that I. Okay, I squared is negative 1. Oops. And negative 1 to the 27th power is going to be negative 1, because negative 1 to any odd power is negative 1. And so I get negative I. With I to the 86, that's already an even number, so I divide it in half. 86 is 2 times 43. I squared is negative 1. And negative 1 to the 43rd power, that's going to be negative 1. I to the 109. 109 is an odd number, so just like the first one, I'm going to break off the last one. So I'd have 108 and then the last one. That 108, I'm going to write that as I squared to the 54th power, because 2 times 54 is 108, and still times that I off to the side. Then I'm going to say, all right, I squared is negative 1, and if I take negative 1 to the 54th power, that's an even number of negative 1s, that'll just be positive 1. So I'll have 1 times I is I. And then I to the 84, I take 84 and I divide it in half, and I get 42. And so thinking about that, oh yeah, I squared is negative 1 to the 42nd power, negative 1 to an even power is positive 1, and that's what I'm going to get there. So that's how I do those. All right, last couple are just, it's a little more arithmetic. So 2 minus 3i times 7 plus I, we're just going to keep practicing our FOIL. 2 times 7, 2 times I, negative 3i times 7. And negative 3i times I is negative 3i squared. Okay, 2i minus 21 is negative 19i. And then negative 3i squared is negative 3 times negative 1 is positive 3. Let's keep collecting, and I get 17 minus 19i. Right, and now this one's, we didn't do too many of these during the unit. I wish we had done more. When dividing by 6i, we could definitely, multiply on top and bottom by negative 6i, multiplying by the conjugate on top and bottom, but it's not totally necessary, and it leads to simplification that we will not need to do if we just multiply on top and bottom by I. Okay, so if it's just some number of i's, if it's not a number that has a real part and an imaginary part, we can just multiply by I over I, and it ends up working out real nice. So if I distribute the I over the 4 minus 12i, I'll get 4i minus 12i squared, all divided by 6i squared. Okay. And then I'm going to have, I'll say that's equal to negative 12i squared is negative 12 times negative 1, so that's positive 12 plus 4i divided by 6 times negative 1 is negative 6. And so 12 over negative 6, that's negative 2. And 4i divided by negative 6, that would be negative 2/3 of I. That's how we would divide one like that. All right, now we're going to plot negative 2 plus 3y and state and graph its conjugate. So negative 2 plus 3i, over here there's negative 2, go up by 3, there's negative 2 plus 3i. And negative 2 minus 3i is going to be the conjugate, so I have to say right there. We didn't really give it a name, so I'll just say, hey, that's conjugate. Equals negative 2 minus 3i. Okay, now we're going to graph the complex numbers. Negative 2i, that right there, that's A. B is 3 plus 2i. C is negative 1 plus I, and D is 4 minus 5i. Those polynomial function has zeros equal to root 7 and 4 plus 5i. What other numbers are guaranteed to also be zeros? None, honestly. I mean, like, looking at this question, there are no other numbers that are guaranteed to be zeros, unless the polynomial itself has rational coefficients. So that's going to be my response to this one, is if rational coefficients, then x equals negative root 7 and x equals 4 minus 5i. But if nobody said anything about the coefficients and they were allowed to be irrational numbers or not real numbers, then nothing would be guaranteed to be a zero of the polynomial. And so I think that's what I'm going to say. If the coefficients are rational, then x equals negative root 7 and x equals 4 minus 5i are also guaranteed to be roots. Next one is find the zeros of this function, write your solution in terms of I if necessary. I think it's going to be, because it's an upward facing parabola with positive y-intercept. It doesn't, not going to have any, real roots. So, okay, zeros of the function. So we say zeros, that's where f of x equals 0. So it's 7x squared plus 21 equals 0. 7x squared is negative 21. X squared is going to be negative 3. I'm going to take the square root of both sides of that equation. So I need to remember the plus minus, square root of negative 3. So that's going to be the square root of 3 times the square root of negative 1, which we're calling I, and so that's going to be my solutions. Okay. Secondary equation, secondary polynomial, 2 zeros, feeling good. Alright, here's a 4th-degree polynomial. We already did these two problems. We're just going to move on. The graph of f is pictured below. If f has 2 imaginary zeros, what's the lowest possible degree of f? Okay, so I've got a single root here and a single root there. If there's 2 imaginary roots, that would be degree 4. Right, the graph of g is pictured below. G is a 7th-degree polynomial. That's also a single root because it's passing through confidently. Okay, one single root, 7th degree, it's going to be 6 imaginary zeros. Because we know that the number of zeros in total has to add up to the degree of the polynomial. Okay. P is a 6th-degree polynomial with a positive leading coefficient. Why can't P have 2 positive, 1 narrow, negative, and 2 imaginary? Okay, because that adds up to 5. I guess it could if one of the real ones was a double root. But I would just say total number of roots needs to equal 6. But if you were sitting there thinking, like, I feel like it could, if one of the real roots was a double root, then, I'd be right there with you. I'd feel the same way. So, if Q is a 4-3 polynomial, why can't it have 2 positive, 1 negative, and 1 imaginary? Oh, it's the 1 imaginary. Imaginary zeros come in pairs. I guess provided that the original polynomial has real coefficients. So, if you were thinking, well, what if Q didn't just have real coefficients, then I guess that could be possible as well. Yeah, and if we allowed Q to have imaginary coefficients, could have that happen. But if Q is going to have real coefficients, then imaginary zeros will come in pairs. This one is going to ask for a sketch of a 4th degree polynomial, 2 imaginary zeros, and a leading coefficient. So that means it's got 2 real zeros. So I would say, something like that. That would be a good sketch. You could also do like 1 double root and 2 imaginary. That's an option you've got. I think those are pretty much the only options, though. Oh, well, I mean, like, you could move around the placement of the other extrema, like that. But either way, you're looking at either 2 single roots or 1 double root and, at most 3 turning points. Alright, so the next ones are going to require us to use our graphing calculator. That's for some other thing I was doing recently. So let's just type in the polynomial. I needed negative 2x, so I'm going to go and insert that 2x cubed minus 3x squared minus 1. I'm going to zoom to the standard window and see, hopefully, it's showing me everything I need to see. All right, so the x-intercepts. Okay, I'm going to compute that 0 that's right there. So we'll calculate a 0 that's between x equals negative 2 and x equals negative 1. Sign change. What happened there? X equals negative 2 to x equals negative 1. Okay, I'm just going to try that again. Buttons I pressed didn't quite take. Yeah, there we go. Alright, so the x-intercept I've got is negative 1.678. Okay, you could say negative 1.677. You can just report the first 3 decimals you see if you like, or you can round to the 3rd decimal place. You just have to be accurate to 3 decimal places. Alright, so the location of a local maximum, I'm going to calculate a maximum. Looks like that's going to be right there. It looks like it's happening at x equals 0. Let's say, negative 1 is to the left of it, 1 is to the right of it. You can even give it a guess of 0 if you think you know what it is. And sure enough, yeah, it's at x equals 0. So let's say at x equals 0, y equals negative 1. Alright, the local minimum is going to happen, calculate a minimum, looks like a negative 1. So, but I'll say it's between negative 2 and 0. Give it a guess of 0. Okay, and then there we've got it. And this is another case, we've seen this a little bit before, where the calculator's got some round-off error, and you have to just, be a human and know that when it says 0.9999998, it means 1. So it's negative 1 and negative 2. Intervals of increase. Okay, it's going to be increasing right there, whereas I move left to right, and I can do that by actually, just like tracing on the graph, just scrolling to the right, and the clicker thing is going up. That means the function is increasing, and that's from x equals negative 1 to x equals 0. Okay. Intervals on which the function is decreasing would be, okay, here, whereas I move left to right, the graph goes down. That's where x is less than 1. And also over here, after x equals 0, right, because if I keep going to the right, the cursor is going to drop down. It's going to start going down really quickly. That's where x is greater than 0. The number of turning points, there were 2. Okay, turning points are extrema, local maxima and local minima. Right, now we've got another polynomial, same job. We're gonna zoom to the standard window, which I think we were already on, and typed it in. Okay, there we go. This one's nice because we're gonna have to adjust the window some, right? I can't see the location of this relative minimum. I know it's gonna be down around there somewhere. What I'm gonna do is I'm gonna go to the window, and I'm going to scroll down so that I get a little bit more negativity in y. So I'm going to go to negative 20 and to 20. You don't need to do that. But, oops. Now I'm graphing. There we go. And it looks good. So I'm going to be finding the x-intercepts. That was the first thing. So the zeros, one's between 1 and 2. So it's x equals 1.597. Other x-intercept is going to be at x equals between 3 and 4. That's 3, 6, 7, 8. Yeah. And then what's after that? The local maxima. That's only that one over there kind of near x equals 0. So we're going to calculate a maximum. That's going to be between x equals 0 and let's just say x equals 2. It's at 0.554. And y at that point is 6.076. Okay, the local minima are going to happen at, it looks like between negative 2 and 0. Negative 0.465 and 4054. Six five 4054, yeah. Okay, that's one of them, but then there's a second local minimum down here at the bottom, what we might call an absolute minimum. So that's going to be number 3 between 2 and 4. That's 2.912. The y-coordinate there is negative 13.13. Okay, now I have a feeling it's just going to be negative 13.130, but I do want to also say, like in this class we need to be accurate to 3 decimals, so it might be good for me to show you how we can see, just like kind of check on this. All right, so what we're going to want to do is, you can do this 2 ways. You can copy down this number to type it in later, but what I'm going to show you is that you actually don't need to, that when you solve for this minimum, it stores this number in for x. So what we can do is we can quit out here, press x, and then look at that 2.912 number. Okay, except we've got all the decimals. What I'm going to do is I'm going to store that into a, because I'll be honest, I'm not totally sure if this works with using x as a number. I think it should, but I'm not totally sure. What I'm going to do next is I'm going to ask for y1, right? So y1 is what we were calling g of x in the problem. And so I'm going to call for y1, and I'm going to basically do g of 2.912 and see what the y value is. So I can call for y by going into variables, y variables, function mode, y1, I can do that. Or I can access y1 by pressing, you can't see that. Let me drag this back. Oh, no, that's not what I wanted. I wanted to move this. And so you can see I'm going to press the green button because I need to access, I think it's F4. Yeah, there it is. And you can access y1 that way if you're working with one of the color calculators like I've got on screen. And then we plug in a, and it's like f of x. The calculator, it knows what you mean. So it plugs in x equals 2.912 in wherever it sees x in the formula for y1. And yeah, and I get negative 13.130. Okay, so feeling more confident about that. Okay, what else are we asked for? Intervals of increase and decrease. All right, so I'm going to go back to the graph. I'm going to say that because I've got, 1, 2, 3 turning points here, pardon me, 3 extrema, I know I'm going to have 3 turning points because that's all the turning points are local extrema, local maxima, or local minima. Okay, the intervals of increase would be between the first minimum and then that maximum. So that would be from negative 0.465 up to 0.554. And then also after the second local minimum, so that's where x is greater than 2.912. And for intervals of decrease, that would be before the first minimum, so that would be when x is less than negative 0.465. And also between the maximum and the second minimum, so that would be from 0.554 up to 2.912. All right, so we filled out that whole grid. All right, the next kind of set of problems is asking all about this function negative x to the 5 minus 4x to the 2 plus x plus 1. I'm going to zoom to the standard window. See what's going on here. All right. I'm going to pause for a second and investigate this a little bit. I've got concerns about what's going on where we can't see it in the y direction. All right, I'm sufficiently convinced that there's nothing, really crazy going on with this polynomial. I am going to enlarge this because all 3 of these problems are going off the same polynomial. So I'm going to find the maxima and minima. So the maximum is happening, it looks very near x equals 0, but I don't think it's happening exactly at 0. So I know it's between negative 1 and 1, though. And yeah, x coordinate of the maximum would be x equals 0.125 or 0.124. And the minimum is going to happen over here between, say, maybe negative 2 and 0. So calculate the minimum. Negative 2 is to the left of the minimum. 0 is definitely to the right of the minimum. And that'll happen at x equals negative 1.209. Or negative 1.208. Intervals on which the function's decreasing. Okay, well, that's going to be after the maximum and before the minimum, so I could probably use those numbers, right? So after the maximum, so when x is greater than 0.125, and before the minimum, which is x is less than negative 1.209, okay, that's when the function is going to be decreasing. Okay, and the intervals on which it's increasing would be between the minimum and the maximum, so negative 1.209 less than x less than 0.125. Right, now, suppose g is a 6th degree polynomial with a negative leading coefficient. Is it possible for g to have 3 local minima? Okay, so 6th degree polynomial with a negative leading coefficient. So maybe we'll just draw like the most extreme version of that possible. 1, 2, 3, 4, 5, 6. No, not possible. The lowest I could see, the most I could see would be 2 minima. If there's a positive leading coefficient, I could have 3 minima. Yeah, that's my reasoning. The x-coordinates of the relative maxima and minima for this one, okay, I was like, I can factor this thing, looks like, But just because we can factor it doesn't mean that's going to help us, and it definitely won't help us find the maxima and minima. We need calculus for that. If we needed to know where this thing was positive and negative, we'd be in business, right? We could factor this thing, we wouldn't need a calculator. But for maxima, minima, increasing, decreasing, we're going to need a calculator. So x to the 3 plus 5x to the 2 plus 4x plus 20. And I'm going to zoom to the standard. Alright. Well, looks like I need quite a bit more in the y direction. I'm not really sure what's going on here. Let's change the window. Let's just change it from -50 to 50. I'm just gonna make sure we're gonna capture it. Then I'll make the scale 5. So it's not totally crowded with tick marks, in the y direction. Yeah, there we go. Okay, so we can see what's happening. It's going up, then down, then up. So maximum, minimum. So calculate the maximum before. Just kind of keep clicking on here until I go to the left of the maximum. Alright, I'd say I'm to the left of it. Then go to the right until it starts to decrease after increasing. And there we go. Alright. Oh my goodness, I did not realize you cannot see that. Oh well. Not worth oh, and then I accidentally right-clicked on stuff. You couldn't see any of that stuff, but I went over here, changed the window to -50 to 50. Okay, that was I think really the only interesting thing I did there. And, did a lot of working around, but then I lost that maximum. What a shame. But I guess I'm not even sure that you saw me do it the first time, so I'll do the maximum somewhere to the left of it, somewhere to the right of it. Give it a guess, and there we go. Alright, so the x-coordinate of the maximum, that's x equals -2.869. And the x location of the relative minimum is going to be over here closer to 0, so I'm going to calculate a minimum. Looks like that's between -2 and 0. And that's going to be at -0.465. Intervals on which the function's decreasing, well, that would be between the maximum and the minimum, so 2.869 is less than x is less than -0.465. Okay, that's where it's decreasing. It would be increasing before the maximum and after the minimum. So before the maximum is, x being less than -2.869, and after the maximum is x is greater than -0.465. Okay, is that all the problems on this review? I'm thinking it is. Yeah, that's it. All right, thanks for watching. Hope this helped.